Hello and welcome to big idea number two. Starting off talking about liquids, solids, the states of matter in general, and we're going to finish up talking about bonding, looking at some of the basic properties, the structures of how we're going to attack each of these formulas and compounds that we're working with throughout the year. So let's go ahead and jump in. Our learning goal, which will be repeated a lot throughout this process, will be for us to understand that chemical and physical properties of materials can be explained by the structure and the arrangement of atoms, ions, or molecules, and the forces between them. So, again, focusing very much on the bonding forces within and without the molecules. Now, intramolecular bonding is the bonding that happens within the molecule, similar to when we hear intramurals, those types of things. It's programs or sports or competitions within the student body. Now, these are usually where we're going to end up with electrons being shared between atoms, or transferring electron is happening within the molecule or within the compound itself. Whereas intermolecular forces are the ones that are going to occur between two separate molecules. Now, we have a couple of different forms that we're going to look at here. We're going to look at dipole-dipole forces, hydrogen bonding, and London dispersion forces. Now, the intramolecular bonds, the covalent ionic bonds, are going to be much stronger than the molecules or the attractions that happen between two different molecules. So you want to keep that in mind as we continue to study. Now, hydrogen bonding in water. If you look at the overall water molecule, we always talk about the fact that it's polar in nature. So on one end we have a negative, and on the other side we have positive. Because I can split this in half and I have each side having its own charge, we say that it's a polar molecule. Now, what do you think is going to happen if I start getting many of those put together? Well, the slightly negative side is going to be attracted to the slightly positive side of another. And eventually we get this network of these compounds that are stuck together. Now, these attractions can be overcome, but they tend to be a little difficult to work with. Now, when we deal with phase changes, we talk about changes in states of matter. When we look at overall phase changes, we're not changing the compound itself, but all we're doing is disrupting those forces that are between or within the molecule or between the molecules. Sorry. So as I boil water, if I go back a slide, you notice we have these attractions between the water molecules. As I begin to heat them up and they begin to move and vibrate back and forth, eventually they're going to get to a point where they can't hold these interactions. And because of that, they're going to change state from a solid to a liquid to a gas, where they'll be spread out all over the place. So this diagram is just basically giving us an idea of what the three states of matter look like at the particle level. Now, when we deal with water in general, we usually look at it in terms of a heating curve, because when we change the temperature and we add in heat or energy, we would expect that it's going to be a gradual increase. But there are a couple of spots that also do something different, and this is what we call a heating curve of water. Now, from negative 20 is where our graph begins. Notice we have a steady incline until we hit about 0 degrees. Once we hit 0 degrees, what happens? Well, if we look at the diagram, it says that we have a mixture of ice and water. Hmm. We'll come back to that a little bit later. After a while, some energy is continued to be put in, and we have just water. Again, steady increase, and by the time we get to the point of water and steam, we flatten out again. That's at 100 degrees Celsius. Now, this time, it's staying flat for a much longer period of time, and then eventually it rises from there into steam. My question is, what happens? Why do you think this happens the way that it does? What's going on here? Now, I want you to just think about that as we continue on through our discussion. Now, as we go from a solid to liquid, we have energy that's added. The particles, begin to move faster. And in doing so, they increase the disorder characteristic of the liquid, or we would say entropy in this case increases. Now, if we go from liquid to gas, which is what we just saw in the graph, we have to add in even more energy. Well, why are we adding in more energy to go from liquid to gas than we did from solid to liquid? Well, to go from solid to liquid, we don't really have to break those attractions that we had before. We simply have to get them a little bit of space so that they can move around. As we go from liquid to gas, we're having to break every single interaction there and to give the water molecules the space they need to completely separate and break those attractions. That's kind of interesting. Now, as we look at water, we see just by looking at the density change how it sort of works. As a solid, we have 0.9168 um, grams per cubic centimeter. As it goes liquid, it becomes more dense at 0.9971, rounded approximately 1. And then as we go to the gas, it gets extremely small. Now, look at the temperature change that we're dealing with from 0 to 25 to 400 degrees Celsius. So, this is at a very, very high temperature, well above the boiling point of water, that our density for water actually drops dramatically. Now, when we talk about dipole-dipole forces, really, usually what we're doing is we're looking at how these two partially charged molecules will interact. When they are attracted to each other, we call this a dipole moment. And this is basically explaining when these molecules, polar molecules, behave as though they're in an electric field. So we have a positive center and we have a negative center, and they're attracted to each other. Now, molecules with dipole moments can attract each other electrostatically, similar to how we will look at it with an ionic compound. They line up so that the positive and negative ends are close to each other. Even in doing this, they're still very, very weak interactions. They're very, very weak attractions. Now, hydrogen bonding is just a specialized form of dipole-dipole force. The hydrogen itself is usually going to be bound to a highly electronegative atom, nitrogen, oxygen, or fluorine, and then it's going to be attracted then to a lone pair from a nitrogen, oxygen, or fluorine on a different molecule. So, again, usually it's because we're having that pull from the nitrogen, oxygen, or fluorine, and it's going to be attracted to another nitrogen, oxygen, or fluorine. And last but not least, we deal with London dispersion forces, or LDFs. Now, LDFs make what we call an instantaneous dipole. Instantaneous meaning it happens very quickly and only for a brief second. Now, this occurs very, very shortly and, like I said, is almost accidentally. And in that process, it actually attracts the electrons from another atom. Now, these are usually going to be the largest when we deal with large atoms or molecules. So the more electrons, the greater chance for that instantaneous dipole, which means the better chance or the stronger the London dispersion force. The stronger the intermolecular forces are, the higher the melting point and boiling point. So if we're looking at certain things that are solids at room temperature, like paraffin wax is actually a nonpolar molecule, but it has such strong London dispersion forces that it actually becomes a solid at room temperature. And we have to heat it up even more to get it to a liquid and then to a gas because those electrons are attracting each other very much. This is giving you an idea of what we're talking about when it comes to the boiling points. Now, this is just looking at hydrides in general. If you note here at the top, these are all the first period, or we say group four, well, broken out by the group, but this is our group two, or period two, period three, period four, and period five. My question is, why is it that these are so much higher than their counterparts, except for carbon, of course? Why is it that ammonia, NH3, has such a higher boiling point than phosphine, pH 3, or arsenic trihydride? What's going on here that actually causes it? And it's all going to go back to what we know about the arrangement of the electrons, the size of the nucleus and the amount of rings, and how that's going to affect the ionization energy and therefore the electronegativity of that element. Now, this is where we're actually going to break for the first part of our video. If you have any questions, please write them down, and we'll continue this in the next one. Have a great afternoon.